All right, so welcome to Math 150, Multivariable Calculus. Oops, this should be lecture 15 or 11. There we go, lecture 15. And so, I see what I did wrong. I switched. I switched those. Okay, there we go. All right. Here. And so what I want to do today is talk a little bit about the chain rule. So this is, I believe, the worst of all the topics in the semester. So once we get through this, we've done the worst of the theory for the semester. How many people remember fondly the chain rule for one-variable calculus? Okay. So that's the beginning point. So in one dimension, you always want to start in one dimension. Somehow reset the thickness. We have, say, a of x is f of g of x, then a prime of x is f prime of g of x times g prime of x. And this part over here, the g prime of x, that's the most forgotten piece of the chain. One way you can try to build intuition is to try to take some simple cases where you understand. So if you can, it's always good to build intuition. So to do that, I need functions f, g, and a so that I understand the derivative of f of g of x in several different ways. So let's take maybe f of x is x to the n, g of x is x to the m. So f of g of x would be what? X to the what? So what would f of g of x be if we have f of x is input to the m and g of x is input to the m? X to the n m. And so now we would get f prime of x is n x to the n minus 1. G prime of x is m x to the m minus 1. And this is going to be our a of x. So a prime of x is nm x to the nm minus 1. When we're trying to evaluate the derivatives, because we have f of g of x, we should be thinking, well, if we're going to evaluate f prime, we can't evaluate f prime at x. If we had f evaluated g of x, so where does it make sense to evaluate f prime? So if we evaluate f at g of x, where should f prime be evaluated? At g of x, that's the point where things are happening. So if we start off with some point, say x, then we go to g of x by applying the function g, and then we apply the function f, and we get f of g of x. And so this is our function a. Start at x, and we go to f of g of x. So when we look at f prime, where should we be evaluating f prime? Well, it should be the same point where we were looking at f, and that's going to be the point g of x. So I should look at f prime not at x, but at g of x, which would be n x to the m to the n minus 1, which is n x to the mn, or I guess n. And so we compare that versus a prime of x, which is nm x to the nm minus 1. Oh, sorry, this is nm minus m. So what's the difference between them? We need a factor. What factor do we need? We need a factor of m x to the m minus 1. And if we were to multiply the f prime of g of x by m x to the m minus 1, that's going to get us to a prime of x. But what is m x to the m minus 1? What is this equal? G prime of X. So this suggests that maybe A prime of X might be F prime G of X times G prime of X. Is this a proof? Not even close. Right. This is looking at one special case and trying to build the intuition, looking at one special case. But it's not a bad special case to look at. It gives us a real good sense of what's going on. It lets us see where the G prime is coming from. It is not unreasonable to say, well, look, my function A involves F and G. So A prime should involve F, F prime, G, G prime in some way. I've got to combine F, F prime, G, G prime in some way. Let me just start writing everything down and see, is there any way I can connect them all? You know, I want to just look at this and do some pattern recognition. So this is a little bit different than how the topic is normally presented. Normally it's presented, you know, a la Moses coming down from Mount Sinai with, you know, the laws of differentiation that was given to humanity by a benevolent deity. We'll ignore the product of Portugal for now. Right? And this is the chain. And here's how you prove it by just doing a lot of algebraic manipulations and multiplying by one and all that clever stuff. What I want to do instead is I want to be like an experimental scientist. You know, let's gather some data. Let's look at some functions and try to see, can we conjecture what the answer might be? And here's the answer. Okay, so what's really going on is we have a function f, which depends on a variable, and then that variable depends on another variable. So sometimes instead of using the same letter, you know, sometimes you might say, I have f of u as u to the n, and g of x is x to the n. Use a different letter for each. They often overload letters in mathematics, which can be, I think, quite confusing. But f has an input, g has an input. It makes sense that if I change x a little bit, g changes. And so because that's changing, then it changes where I evaluate it. And so we have to go through, we have to rigorously prove that this is the case. So in the lecture, I go through the proof in one dimension by multiplying by one and doing the analysis. I want to just put a few notes over here about some of the dangers. So we have to be a bit careful. Let's let a of x be f of g of x. And let's go back to the definition of the derivative. So a prime of x is the limit as h goes to 0 of f of g of x plus h minus f of g of x over h. Where does this kind of look like we're evaluating the derivative? What point does it look like we're evaluating f? Yeah, imagine, and this is not true, imagine that g of x plus h equals g of x plus h. We then get the limit as h goes to 0 of f of g of x plus h minus f of g of x over h, which is just f prime at g of x. And in fact, you can see that this lie is what's responsible for the missing of the g prime. So just to make sure that there's no sense of confusion, this is of course false. This is not true. You cannot do this. G of x plus h is not g of x plus h. But if it were, then it would be, I'm just evaluating. So the question is, what is g of x plus h? So let's try to, you'll think about g of x a little bit. This is one of my favorite theorems in all of mathematics, the mean value. So f of b phi of b minus phi of a over b minus a equals b prime of c for some c in the interval a. So you give me a nice function, the average speed equals the instantaneous speed at some special point. So the average speed is the instantaneous speed at some special point. We don't know where that special point is. For a lot of things in pure mathematics, it's actually okay that we don't know where that special point is. We just need to know it's such a special point, and we can make these arguments. Okay, so let's see what's going on. Let's look at g of x plus h minus g of x over x plus h minus x. So here, let's figure out what is a, what is b, and what is our function phi. So what is the point a in this case? What would a be? A would be x, b would be x plus h, and our function phi would just be our function g. And so by the mean value theorem, this has to be g prime at some point c. I'm going to call it c sub h, just to remind myself that the point depends on h. I could call it, c sub h comma x to remind myself that it depends on both x and h. So what's x plus h minus x? That's just h. So I can rewrite, and this becomes g of x plus h equals g of x plus g prime of ch, g prime of ch times h. So notice how close that is to what we had before. Before we said, let's just say g of x plus h is g of x plus h. I can just pull the h outside. This tells me how it changes. It changes by this extra factor g prime of ch. Which makes sense. This is the tangent line approximation. I start at g of x. My instantaneous speed is g prime of x times h. And that would give me the tangent line approximation. I'm not doing the tangent line approximation. What I'm doing instead is saying the mean value theorem tells me that it equals this. But this should be very close to what? This is very close to g prime of x. That the error in replacing that with g prime of x is very small. And that's what's really going on in the proof of the mean value theorem. It's exact if we use the special point c, which we don't know where it is, but we know c lives between x and x plus h. So if this is x and this is x plus h, then c sub h has to be somewhere in here. So as h goes to 0, c of h goes to what point? It has to go to x. So this is a really close approximation to the tangent line. The tangent line is not the truth, it's close to the truth. And so I want to just be really rigorous now. I want to start writing down what I have. I've got f of g of x plus h minus f of g of x over h is f of g of x plus g prime at ch times h minus f of g of x over h. And now what I'm going to do is I'm going to multiply by 1, g prime c of h times g prime c of h. This looks like the derivative. So as h goes to 0, looks like f prime at the point g of x. And this looks like g prime of x. Because as h goes to 0, c of h goes to x. So the important thing to note is if a limit exists, does it matter how I approach? So if the limit exists, can I approach any way I want and I get the same answer? Yes. If the limit doesn't exist, does it matter how I approach? Yes. Because f prime is differentiable, any path I take that gets me to g of x has to have the same limit. And so why not just take the special path? And so if I take the special path, this is a special path, and now I've got the same little boost in where I'm evaluating f in the numerator as I have the difference in the denominator. You know, instead of having h, I have g prime c of h. So here's your chance to get some extra credit points. What do I have to be afraid of? What is the danger? H would never be zero. We've always agreed H gets closer and closer to zero without it being zero. You're close. Yes. So what if g prime of c of h equals 0? Well, there's two ways this could happen. One is that it can happen only a few times. If it only happens a few times, then eventually when h is sufficiently small, we never have to worry. So does everyone agree that if it only happens a few times, we're okay? So case 1 only happens finitely often near x, so we're okay if h is small. What's case 2? Okay, but there's other ways. That's one way, but there's other ways. So case 1 is if g prime is 0 only finitely often. That's not the next case. There's something in between that happens finitely and it happens every single time. Yeah. So infinitely often g prime of c of h equals 0 as h goes to 0. That's the troublesome. But notice we're multiplying by g prime of c of h, which is 0. So if you're in a situation where the function's derivative, where g prime vanishes infinitely often, you have to be a bit careful. I'm going to just give you an example of such a function so that you know stuff like this happens and that you are aware of it, and then we will never speak of it again. All right. Any Simpson fans here? Who is the principal of Springfield Elementary? Which one? Who knows what I'm talking about? What am I talking about? No.
Like he came back from Vietnam, like
He assumed someone else's role, so he's not the real Skinner. But his mother actually likes him better than the real son. And so they just said, we're never going to speak of this again. So it was only in one episode, but Skinner is not Skinner. The Cleveland Browns are not the Cleveland Browns, you know, your football history. So I will just mention this function so that you are aware that it exists, and then we're not going to talk about technical issues like this. Let's let g of x be x cubed sine of 1 over x if x does not equal 0, and 0 if x equals 0. Okay. If you want to take the derivative of g prime of x, the only point where it's hard to take the derivative is when x equals 0. If I take the derivative away from 0, what rule do I use? Product. So I would get 3x squared sine 1 over x minus derivative of 1 over x becomes negative x to the minus 2. So it would be minus x sine 1 over x if x is not 0. And if you actually do the calculation with the limit, you get 0 if x equals 0. it turns out that this can equal 0 infinitely often. So we have some real dangers we need to look at. Or maybe I could choose, or I could choose maybe x cubed sine of 1 over x to be my function. Let me just quickly plot this.
Like the second term minus x cosine.
Oh, yes, thank you. Derivative of sine is cosine. So let's plot. So I can zoom in. See, go from 2. So let's start to zoom in a little bit. Start to zoom in, you can just see the absolutely wild behavior. Yes. Well, it's actually not a discontinuity. The limit exists at 0. If I didn't have the x cubed, you would have some kind of discontinuity.
It's not differentiable.
It is differentiable. The derivative is 0 at 0. So we can plot the derivative. Plot the derivative. It was going to be 3x squared sine of 1 over x minus x sine of 1 over x. If you think about what's going on, when x is small, which is bigger, x squared or x? X. And so it's really bounded by the lines y equals x and negative x. When x is very small, the 3x squared is negligible relative to the x term. And so it's basically hopping back and forth between those two lines. So when you zoom in, you see you absolutely wonderful behavior. This is the power of being able to use software like this to just get a quick sense. Functions like this exist. I have given you a function that has infinitely many zeros, and its derivative has infinitely many zeros in an arbitrary small neighborhood of 0 where the action is happening. So this is to just let you know that we do have to be careful when we develop the theory for stuff like this. Or you can just say we assume that our functions do not have these properties. And if you do that, then it's much easier. But I always want you to be aware of when I'm trying to gloss over something. Okay. So I'm going to go back down here and share this one. Okay. So this was to just give us a little bit of a warning of what can go on. And so this is the danger. So can have situations like this where you have many zeros. Okay. So now let's go on to several variables. So we have some point here, let's say x and y. So we have something with two variables. We then apply a function g, and maybe we get a triple. U, V, W. And then we apply our function f, and we'll get a number. So what we have is f takes 3 inputs and gives us back one output. G takes 2 inputs and gives us back 3 inputs. So f composed with G takes 2 inputs and gives us back 1 output. So you always want to get a sense of where do you start, where do you end, what's my input space, what's my output space. And so here I start with 2 points, x and y. I then apply g, and I get 3 points. I get a triple UVW. Okay. And so now, let's look at what's going on. So I have, f of u, v, w is f of u of xy, v of xy, z of xy. Oh, wait, was I doing, I'm sorry, I was doing UVW, right? So I have a function of 2 variables. I can regard this as the function, call this a of xy. So a takes 2 inputs, it gives me 1 output. So I can compute dA dx, and I can compute dA dy. These are just the standard partial derivatives we know how to do. It took us 1 minute to learn how to do partial derivatives because of our calc knowledge. If I want to take the partial derivative of a with respect to x, just pretend y is a constant. That's it. Now what I want, though, is I want to write the partial derivative of a in terms of partial derivatives of f and partial derivatives of u, v, and w. So this is very similar to your chemistry class, where you're trying to break a complicated compound into simpler pieces, maybe all the way down to the atoms or whatnot. You want to take something complicated, break it up into simpler pieces. Hopefully F and U, V, and W are easier to understand, and then by knowing how they vary, we can use that to piece together how A varies as a function of X. One thing that's important to note is the way we've written it right now, we don't have F of G of Xy. So I'm going to define G of xy to be the following triple: U of xy, V of xy, W of xy. And now I do get A of xy is F of G of x. Because if I write it as F of U, xy, V, xy, W, xy, it's not of the form F of G of x. And I guess here I should be using xy, not just x. And so now this really does look like a generalization of the chain rule in one dimension. In one dimension, I had F of G of input. Now I have F of G of input. And just my input is just written in a more complicated form. It's just of the form U of xy, V of xy, W of xy. And the goal is knowing how U, V, and W change with respect to x and y, and knowing how F changes with respect to U and V and W, can I figure out how this compound A changes? So the goal, input is how U, V, W change with respect to x and y. Input, how F changes with respect to U, V, W. Output, how A changes with respect to x and y in terms of above. And if you think back to how we started today as experimental scientists trying to sniff out what would be the chain rule by looking at certain cases. It makes sense that our inputs, so A of xy is F of U xy, V xy, W xy. dA dx and dA dy should involve df du, df dv, df dw at the point u vw, and also du dx du dy, dv dx, dv dy, dw dx, dw dy at the point xy. So it's always remember, where are we evaluating? We evaluate f at a triple UVW. So when I calculate the partials of f, I've got to be evaluating it at UVW. UV and W then depend on x and y. So when I calculate those partials, they should be evaluated at the point xy. And we get the following, really nice formula. So theorem notation as before. dA dx is going to be df du at the point I'll call it g of xy times du dx at the point xy plus df dv at the point g of xy dv dx plus df dw at the point g of xy times dw dx. And then similarly for dA dy. If you look at it, you almost want to say, well, can I just cancel out the du's diagonally and cancel out the dv's diagonally and cancel out the dw's diagonally? No. But if you use this to try to remember, I first see how f changes with respect to u, and then I magnify that by how u changes with x. And that's similar to what we were doing at the beginning of the day. So, we have to remember, where's that g prime of x factor coming from? When I write g of x plus h, it's g of x plus g prime times of h, not just g of x plus h. H has to be magnified by a little bit to take into account as I change x to x plus h, g of x doesn't go to just h more than g of x. The amount it goes is dependent on what is the instantaneous speed, essentially, at x. And that's really g prime of x times h. It just happens to be exact when I use this point c sub h, which is almost the point x. Okay? So going down over here, some of the slides is actually showing the text on the left and some it's not. Okay, so over here, so when I look at dA dx, I want to say, well, first of all, how is f changing with respect to the first coordinate u? And that's my df du. And then I magnify that by how u is changing with x. So in the video, I go through and do this in much greater detail by going through and looking at, well, let's just calculate it the long way. So, dA dx would be the limit as h goes to 0 of f of u of x plus h y v of x plus h y w of x plus h y of h minus star. I'm just running out of space, where star is just going to be f of u of xy, v of xy, w of xy. And then what we do is we basically do a sequence of points. So we start off at the point u of xy, v of xy, w of xy. And then I go from here to u of x plus h, y, v of x plus, v of x, y, w of xy. And then I go from here to u of x plus h, y, v of x plus h, y, w of x plus h, y. And then I go from here to u of x plus h, y, v of x plus h, y, w x plus h, y. I keep adding one more component. And so the whole idea is I can now take my fraction and just subtract 0 or add 0 in a very clever way. And so what we're doing is the numerator is going to be f of u of x plus h y, v of x plus h, y, w x plus h, y, minus f of u of x plus h, y, v of x plus h, y, w of x, y. And now I add back what I just subtracted, f of u of x plus h, y, v of x plus h, y, w of x, y. And now I subtract f of u of x plus h, y, v of x, y, w of x, y. You see it's getting simpler and simpler. Now I add back what I just subtracted, f of u of x plus h, y, v of x, y, w of x, y. And now I just remember I initially had to subtract off f of u of x, y, v, x, y, w, x, y. So I've added 0 twice. And if you look at what's going on over here, notice that the second and the third components don't change at all. Because the second and the third components don't change at all the action is happening in the first component. And so when I look at this change, when I divide by h and I take the limit, this is going to look like df du at my point, g of x, y. And then I have to take into account, the du dx. It's just the one-dimensional chain rule. And so in the very last one, the last one is the easiest one to look at because the v and the w's are not changing at all. So I really don't need to regard f as a function of 3 variables. At this point, f is just a function of one variable because I'm keeping the v and the w parts the same. So when I write df du, it's really just the standard derivative of that original function. And now because y is fixed as well, it's just the standard chain rule where instead of the function g, I'm calling it u. If I look at the second one, if I look at the blue minus the red, we notice that they both have the same third component. They both have the same second component, but they have a different middle component. So the middle piece is going to look like df dy at the point g of x, y times, I'm sorry, df d v, sorry, df dv times dv dx. Because again, the first and the third components are fixed. There's no change in the first and the third components. So I can really regard it as a function now of just one variable, the middle. And while the middle looks like it involves 2 variables, x and y is fixed. So it's really just my function u is my function g from the one variable g. And now I just have my very last one. And then this last one is going to just be df dw times dw dx. So this is where the one variable chain rule gets magnified up to several dimensions. We had to subtract 0 in a clever way. And this is why I wanted to switch to the iPad today, because it's just easier to get to all the different colors from it. And the more colors you can see, that you can really see what's going on. We've done nothing. Painfully for many minutes, but we've done nothing. We've just added 0. Okay. Why is this valuable? Because by adding 0 in a clever way, we can now recognize some of the terms as expressions that we like. And that's where this formula comes from. And so now we get this result of this is the change. If I want to figure out how does A change with respect to X, it's how F changes with respect to U magnified by du dx, plus how F changes with respect to V magnified by dV dx, and then how F changes with W magnified by dW dx. And so if I give you complicated functions, I can now hopefully figure out what the complicated functions are doing in terms of the simpler ones. Yes.
So we said this is what the numerator of like the limit simplifies to.
Right. And so when I'm putting in all the stuff over here, that includes dividing by h and taking the average.
Okay.
There's just sadly not enough room to put in the h's. It's compressed enough as is. I probably should have actually changed the thickness of the pen. If I was teaching 2 sections this year, that's what I would have done for the second section. So I would have decreased the pen size so that I could squeeze it a little bit more. But the idea is, if you look at the numerator, it's initially just the 2 black terms, one minus the other. Where the first one has all of the x components at x plus h, and the second one has everything at x. And then by putting in all these intermediate points, we can always focus where the change is. So we're really going in a grid manner, going this way, to that way, and moving in very nice ways to get from point to point. But now that we have this, we can use this. Sometimes, rather than using the chain rule, what do you think might be easier? So let's say we have x equals r cosine theta, y equals r sine theta. So these are my polar coordinates. And I have some function f of xy is x cubed plus xy. And so I can get some new function of r and theta, which is going to be f of x of r theta, y of r theta. So dA dr is going to be df dx dx dr plus df dy dy dr. Right? That's what the chain rule says. Okay, let's calculate. If x equals r cosine theta, what is dx dr? So what would dx dr be if x is r cosine theta? Just cosine theta. I don't need to calculate what dx d theta is if I only care about dA dr. But I could if I want to, I don't. What is dy dr? Sine theta. Okay, what about df dx? What's df dx? X squared plus y, and then df dy would just be x. So if I substitute, this would equal df dx is going to be 3x squared, but x is r cosine theta, plus y, which is r sine theta, right? That's my df dx. Does everyone agree that that's df dx? What's dx dr? That's just cosine theta. Plus df dy. Df dy is x, but what's x in terms of r and theta? Just r cosine theta. And then we multiply that by dy dr, which is sine theta. And so we get 3r squared cosine cubed of theta plus we have r sine theta cosine theta r cosine theta sine theta plus 2r cosine theta sine theta. Do we agree? Is there any way we could check our work? So A of r theta is f of x of r theta, y of r theta. F of xy is just x cubed plus xy. So A of r theta is just going to be, okay, I put in for x cubed, I'll just get r cubed cosine cubed theta. And then the xy is going to become r squared cosine theta sine theta. So what's just dA dr? It's just going to be 3 r squared cosine cubed of theta plus 2r cosine theta sine theta. So it checks. Sometimes it's easy to just substitute in, right? If I want to know how does A depend on R and theta, if I'm able to just plug in, that's great. You're not always going to have explicit formulas. So sometimes you might have, I know how F is changing, and I know at this instant, X is changing at the following rate, but I may not have the full functional dependencies. How many of you remember these related rates problems from calculus? You've got water is falling into a cylinder. Okay, well, that's not too bad. It's a cylinder. How fast is the volume changing? Not a big deal. Now it's falling into a cone. How quickly is the water level rising in the cone if the water is falling at a given rate? And so you often have how one thing is changing, and you want to pass from that to how something else is. This formula for dA dr, it tells us if I know how F is changing with respect to its inputs and how X and Y are changing with respect to R and theta, I can then use that to figure out how A is changing with respect to R and theta without actually knowing explicitly the function. If you just happen to know these instantaneous changes. Right. Any questions about this? All right, so this was definitely the most theoretical, painful lecture of the semester, and it is good to get this over.